Good morning, students. Let's begin with our new chapter, that is nuclear physics. So, nuclear physics deals with the nucleus which is present inside the atom. We know that if an atom, the range given is 10 to the power minus 10 meter, then for the nucleus it will be the nuclear range will be 10 to the power minus 5 meter. So you can understand the differences of minus 5 means the nucleus is nearly 1 lakh times smaller than the atom. After that we see that what do we mean by nucleons. So when we talk about nucleons, these are the combination of protons as well as the neutrons. The protons have the positive charge, neutrons have zero charge, overall charge. The atomic number. So what is atomic number? It is the equal to the number of protons. When you talk about the mass number, it is actually the number of neutrons and the number of protons. When you talk about the nuclear size is denoted by R, which can be the radius. So it is directly proportional to 1 by 3 of A. But when we remove the proportionality sign, we get this R0. This R0 has a constant value, that is 1.1 multiplied by 10 to the power minus 15 meter. Means this A, which was our mass number, if this changes, then we can say that the nuclear size may also change. Now when we talk about the nuclear density, it is mass upon volume, but when we see for the small nuclei, this is nearly 2 constant and its value is 3m upon 4 pi r0 cube. Now let us talk about the atomic mass unit. So what do we mean by atomic mass unit? So atomic mass unit is actually equals to 1 by 12 of the mass of carbon 12 isotope. What is the mass of carbon 12 isotope? 1.99 multiplied by 10 to the power minus 26 kg and its 12 part. So it will be equal to 1.6 multiplied by 10 to the power minus 27 kg. If you are familiar with this number, you have seen it. It is actually the mass of proton as well as of neutron. Let us talk about now isotopes, isobars and isotones. So what do we mean by isotopes? So first let us talk about the isotopes. So isotopes are those which have same atomic number, but we talk about then they have the different mass number. Now over here if we talk about, so here the isotopes of there are 3 isotopes of hydrogen which you can see. So the 3 hydrogens are protium, deuterium and tritium. You can see that the mass number are 1, 2 and 3. Now when we talk about the isobars, isobars are those which have the same mass number, same atomic number, but they can have same mass number but different atomic number. For example, if we talk about over here, so here there are hydrogen as well as the helium. When we talk about their mass number, so what could be their mass number? Their mass number is 3 and 3. But when we talk about the atomic number, so atomic number over here is 1 and 2. So these are the isobars. Similarly is of sodium and neon. When we talk about the isotones, what are isotones? Isotones are those which have the constant difference of mass number and the atomic mass. Means when we subtract this 3 from 1 we get 2. Here also 4 from 2 we get 2. So these are isotones. Similarly of the carbon and oxygen also. Let us talk about the isomers. So what do we mean by isomers? We have talked about isotopes, isobars, isotones, but these isomers are really different. They are having same atomic number, they are having the same mass number, but their radioactive properties will be different for different elements. Now what we talk about the nuclear force. What is a nuclear force? It is the strongest, means in whole universe the strongest force is the nuclear force, and it exists between the protons and the neutrons. So the nuclear force is always existing between the protons as well as the neutrons. Now let us talk about what do we mean by mass defect. So what is mass defect? So whenever we observe the number of nucleons, so the total mass of the nucleons that we observe in a nucleus is something, and if we measure the mass of the nucleus, now we know that the nucleus is only comprised of nucleons. So we can say that the mass of nucleons and the mass of nucleus should be equal. But when we experiment it and we find out practically, separately of mass of nucleus and mass of nucleon, we find that they are different. So we find also that the mass of nucleus is actually less than the nucleon's mass. So that is a defect, and this is only called as mass defect, denoted by delta M. So now what is the formula of this? It is Z, which is the atomic mass, atomic charge, MP, which is the mass of the protons, plus A minus Z. A is the mass number, Z is the atomic number, multiplied by Mn, which is the mass of the neutrons, minus mass of the neutrons minus M capital N, which is the mass of the nucleus. So this is the here this capital M will denote the mass of the nucleons, and this small m will denote the mass of the nucleus. Now let us derive the mass energy relationship. So we know that what is the mass energy relationship according to Einstein. It is E equal to mc square. So what you have to do is you have to replace this mass defect value into this m, and you will get your answer. So whatever is the value of m, that is Z mp plus A minus Z mn minus M capital N, and over there you will write c square. So this will be the mass energy relationship. Now let us talk about the nuclear binding energy. So what is nuclear binding energy? It is that energy which is required for a nucleus so that we can separate its nucleons and bring them to the infinite distance, so that they have no force of attraction between each other now. So what is the nuclear binding energy per nucleon? So it is the nuclear binding energy upon the number of nucleons. Means whatever is the total nuclear binding energy that we have told, that is a force of attraction, and which we have to separate upon the number of nucleons, means the number of protons plus neutrons. Now what is the packing fraction? So packing fraction is actually the nuclear mass. Nuclear mass is the mass of nucleus minus the mass number. This mass number is the nucleon mass only, because mass number comprises of protons and neutrons, and nucleon also consists of protons and neutrons, upon the nuclear mass. When we talk about it is M minus A, where this M and A are nuclear mass and the nucleon mass upon M, which is again the nuclear mass. Now let us talk about the binding energy curve of the different types of atoms. So this is our nuclear binding energy curve. You can see that on the y-axis we have the average binding energy per nucleon, and on the x-axis we have the mass number. Now what do we observe? We should start observing from the lowest point, that is from the deuterium, which is 2H, that is given over here. Now what can we see? It has the lowest binding energy, and its atomic, that is its mass number, is also lowest. Means here it is the easiest to separate the nucleons, so it has the lowest binding energy. This one is having the lowest binding energy. Now as we go above, what do we see? That from the atomic number 50, means when you talk about from here to here till atomic number 80, what do we see? That here is the highest binding energy. So here it will be the highest binding energy, and the mass number are also low. But here we can see that the iron and arsenic, which are among these, have the highest binding energy. As you can see from the graph of the y-axis, that these are having the highest binding energy. But after this you can see that there is a decrease among the binding energy in all of them. Means here what we see is the decrease is gradual in the binding energy, because as the mass number is increasing, their binding energy is consequently decreasing. Means what we can say is here for these, that the mass number is inversely proportional to the nuclear binding energy, but it is only applicable for those elements whose atomic number is greater than 80. For them only we can say that the nuclear binding energy is inversely proportional to the mass number. Now what we can say, what we can conclude from this graph, we can say that it is because hydrogen has the lowest nuclear binding energy, it has the lowest nuclear binding energy, means here the energy that we have to provide will be the least, means we can easily separate the nucleons and bring them to the infinite number of distance. Now you can see there is a peak for this helium, for this neon. Why is it so? Because these have the stable octet, and because of that they have the high binding energy. Now after that we can say for the iron and arsenic we will require the high, as it has the highest binding energy, therefore we will require the highest amount of energy to separate them. Also when we talk about for those elements which have the greater atomic number than 80, so here you can see that the average binding energy per nuclei is decreasing, and the nuclei of heavier elements or these heavier atoms, now what are they behaving as? They are behaving as radioactive. Like you can see for this bismuth, so now it will be radioactive because its nuclear binding energy is now less. What does it mean? It means whenever we talk about the element to be radioactive, it means that we are decaying its nucleus, means its nucleus is getting splitted into the nucleons. Now even nuclei are more stable than the intermediate neighbors, which we can see that some of them are more stable, the even nuclei, and the odd nuclei are less stable. And we can also see over here that if 2 is stable, then there is 4 stable, there is 12 stable, means even number of nuclei are more stable than the odd number of nuclei. Also the nuclei having the mass number below 20 are comparatively less stable than those of above, because they have the less nuclear binding energy. Now after this we should also say that which of them are the most stable among the all and which of them are least stable. So let us talk about them. So out of all those atoms which we saw above, the most stable will be those which contain the even number of protons and even number of neutrons. You know that the number of nucleons will be equal to protons plus neutrons, and if this is even number, this is even number, you can say that this will also be even number. So those of even atomic mass, those of even mass number are stable, and least stable or less stable are those which are having the odd number of protons and neutrons. We also know that if the electrons are odd, means they are unpaired and they will be now less stable. Similar is the application to these neutrons and protons also. If they are odd, it will simply mean that they will be least stable as compared to the other ones. So with this we have done the first part of this chapter, and tomorrow we will going to discuss about the nuclear reaction.